pressure, but it's something that we do consider. We have to design for external pressure, and it's a big consideration on very thin vessels and large diameters. But I did kind of skip that part. We have to design for any superimposed static loads, reactions, weights, other equipment that might be on the vessel, machinery, pumps, whatever, heat exchangers, any of those things, any kind of internals. We have to design for the supports, lugs, whatever, any kind of support system. And then, like I said, cyclic dynamic loads, wind loads, seismic, impact, shock, temperature gradients, all those things. Those things all have to be considered as part of the design. Go ahead. And this is just a list of types of loads. We have steady loads, so that's long-term duration. Internal, external pressure, dead weight. And these are all the things that you see in the vessel all the time. So you have vessel contents, loading due to attached piping and equipment, loadings to and from pipe supports, thermal loads, wind loads. Now the other thing is short-term duration. So that's the kind of things that happen as events. So shop and field hydro test, an earthquake, erection, transportation, emergency, thermal loads, and startup and shutdown. So all those things are things that are just going to happen as an event, and you're not going to see them all the time. Okay, so going on. Again, we were talking about ladders and platforms. Ladders and platforms are a part of what is required in UG-22 because all these loads, now the structural person will know, all the platforms are designed for basic loads, say 75 pounds per square foot. That's that's a typical required load that a structure has to be designed for human occupancy. So every platform has to be designed for that, plus the weight of the steel itself. So you add all that up, and then you have to figure out what kind of load that puts on the clip on the vessel and how that is imposed on the pressure and the bending, and all those things have to be added up to determine whether the clip is acceptable for the load. So these are all things that we design for, and it's something that has to be considered as part of the design. Go ahead. In addition to that, we get loads at all the nozzles. So Pipe Stress does a pipe analysis, and those loads are imposed on the vessel. So this is the types of loads that we see on the vessel on any particular nozzle. So you have a circumferential moment, you have a torsional moment, and you have a longitudinal moment, and then you have the forces that go along with those moments. So all those things are added up, and you take the combined loads, and then you take that and look at the stress in the vessel, and you combine those loads with the stresses due to the internal pressure, bending, all those things to determine whether the vessel is capable of taking that load. So it's not an easy thing, especially when you get vessels that are large in diameter and thin shell. So go ahead. This is an example of what actually happens to the vessel due to local loads. So as you can see, if you have a inward force, it wants to bend locally around your clip. If you have a circumferential moment, it wants to bend towards the one side more and then pull tension on the other side. And the same way with a longitudinal moment, it wants to bend in on one side and out on the other. So go ahead. This is a little bit of the same thing, but this is kind of a moment diagram. But it kind of shows you if you have a moment, starting from the left, if you have a moment applied to the vessel, this is what it wants to do to the ring. So this is the forces that the ring or the shell wants to the force results in from that force. So like you have a tangential force here, this is what the ring wants to do. You have a radial force here going out. This is the result of the ring. And if you have a radial force inward, this is what you get. Okay, wind design. So if we get very tall vessels sometimes, and like we showed before, it's a tall and thin structure. So you have to analyze the vessel for the wind loads, and it may not be the load that's governing. A lot of times seismic loads govern, but you have to look at it both just so you know. So we have what we're looking at here. We're going to look a little bit at the building codes, UBC 97, in some of the examples coming up. And the reason I'm doing that is because that's still the building code for California. However, there's a lot of other building codes out there. You have IBC 2003, which is is used in Alaska, and there's Southern Building Code, and there's a few others out there. But anyway, this is the basic requirements. You have to check the forces, and you have to check it by the area on the vessel. So you can go ahead. This is a little chart, and what it shows you is that these are kind of old numbers, but basically what they're showing you is if you have flat terrain, this curve is flatter, and your wind forces down lower are higher. As you have trees and stuff in the way, or you have buildings, you can see this curve gets steeper up, and so the wind loads are less at if you have a building or a structure here, your wind loads here are going to be lower than your wind loads over here because this angle of this line here is a little bit flatter here at the bottom, and then as you can see, you go to the building and it's even a little steeper up. You can go ahead. This is how we check the loads on any particular vessel. So if you have forces at each elevation, and you take these forces as the wind pressure increases as you go up the side of the vessel, then you take a look at each section, and you design each section, and then the moment is the combined moment of all these forces together at the base. And likewise, this is true for a horizontal vessel, and then this is how it would be applied to a vessel on lugs and a vessel on legs.
So this is okay, right?
I'm sorry?
Consider vibration, like wind vibration in design?
Yeah, if we have some vortex shedding, especially, yeah, we do. But most of the design is a static design by code. The code is based on static design. Okay, go ahead. This is just a little chart from UBC 97 that shows you the wind zones. So as you can see, down here in Florida, the design wind speed is 110. We're over here in the 70 to 80 mile an hour range. And, it varies. These are some special areas here where you have higher wind speeds. Okay, seismic design. Seismic design is similar because it's still a static design. And these are based on work that was done in the past where they tried to figure out what kind of loads would result when you have the shaking. In reality, the static design is based on horizontal forces and static design. But as you can see over the years, something that's interesting, in 1927, the basic formula for horizontal shear was 10% of the weight of the structure, or the mass of the structure. Up through 1955, it was still 10%. Then in 64, it went up to 13.3. And then in 76, it went up to as high as 28% of the mass. And then, as you can see, in 88, it went up to almost 37%. And in 97, it can be as high as almost 73%. So it's substantially higher today than it was you know, back in 1927. So it's a long time, but there's a big difference here. This has a little more. You very rarely see it this high because there's a lot of different factors that contribute to what this value is going to be. But as you can see, the potential for an earthquake and the emphasis on design has really changed over the years. Okay, so if we're looking at an earthquake, what should we be considering? Well, from the strict basis of the earthquake, you know, you have to really know what the magnitude is, the direction of the motion, the distance from the epicenter, soil conditions, general geologic conditions, and the response of the structure itself. So from our standpoint, this is really the biggest issue. What's the response of the structure itself? And for vessels, the direction isn't as important because usually they're round, you know, so it doesn't make as big a difference. But horizontal vessels, it could make a difference. So go ahead. This is just a chart that shows you the main areas. As you know, this is the Ring of Fire, where you have the biggest earthquakes in the world is right through here and through here are the most volcanoes and that sort of thing. So this is where this is your biggest areas of concern. Not that there aren't bigger areas. There's big areas everywhere, but these are a couple of the biggest areas. This is a little bit on types of faults. So you have a strike-slip fault. This shows you what the directions are. They're going opposite sides. Here's a normal slip and a reverse slip. So you can see a little bit what the differences are here. Okay, this is a little bit of again, very similar to the wind design. But it's the same kind of thing where you have to, this is a single section, so we calculate, we find the center of the load, and we calculate the overturning moment based on the forces. These formulas are a little old, but the basic idea is here. And the same is true here. As you can see with this vessel here, we have a reboiler over here, heat exchanger, and that all contributes to the overturning moment. So those are all things that have to be considered. So go ahead. And again, here's a chart for seismic zones, and so we can you can see what those are. So go ahead. Okay, we're going to fabrication of vessels, and I'm going to have Hong Lim come up, and maybe should we take a 10-minute break? Take a 10-minute break.